So today we're gonna start on the alkyne chapter, which is chapter 13. First, let's go over the acidity of these hydrogens. So which one of these color-coded hydrogens do you guys think is the most acidic? The right one, the green one, because of what factor that makes this hydrogen the most acidic? Yeah, more S character, that's right, because that carbon right there where the hydrogen is attached to is sp hybridized. And so we see that these blue hydrogens here are sp3 hybridized. These purple hydrogens here are not like they're all of the hydrogens are s orbitals, but they're attached to a carbon that is sp2 here, sp3 here, and sp here. Right? Where the more s character the hydrogen is attached to, the more acidic it is. Right? So more s character means that the orbital is closer to the nucleus, and the nucleus is positively charged because it's consisted of protons. And since it's more like close to the nucleus, closer to the positive charge nucleus, the carbon is more electronegative, making the hydrogen more acidic. Right? Where the pKa of an sp3CH is around 50. The pKa of an sp2CH is around 44. pKa of an SpCH is around 25. We see that the pKa decreases as we increase S character, which means that it's becoming more acidic. Right? So now let's go over how to make alkynes, triple bonds. So let's review an alkene reaction. What will this reaction do to the alkene here? Br2 and CCl4. Syn-addition or anti-addition? Anti-addition, right? We will add bromines on both carbons of the alkene, anti to each other. Right? And so we know that this is a single bond, which we could rotate and give this same exact structure here. This structure is the exact same structure as this. I just rotated the single bond between here, those two carbons, right? Which inverts this dash bromine into a wedge bromine right there. Okay. Now we could use that vicinal dihalide to do E2 reaction. So E2 reaction requires what kind of reagent to make a double bond? We have a good leaving group, and what is usually the reagent on the arrow that makes E2 reaction happen? A strong base, strong nucleophile, right? So in this case, the strong base that we're going to use usually is NaNH2, right? And we are going to need at least two equivalents. So you can see two equivalents or excess, meaning that we have a lot of them, but we need at least two. And this happens under NH3 liquid. That will create an alkyne, a triple bond between these two carbons right here, holding the bromine. Right? So the mechanism here is going to be E2 two times. So let's draw in that vicinal dihalide. And we know that this beta hydrogen here is anti to this leaving group. So the strong base here can deprotonate that hydrogen, make a double bond there, and kick out that leaving group. That makes your alkene here, right, after the E2. We see that this carbon here is now sp2 hybridized, which is why this wedge bromine turned into a flat and planar bond. Right? We also have a beta hydrogen that is anti to this bromine and a second equivalence of NH2 minus. This is the first equivalence. This is the second equivalence. We're going to do E2 one more time. Grab that hydrogen, make a extra bond there, kick out that leaving group, and form your extra bond. But what is the bond angle of alkyne? Yeah, 180 degree, meaning that they have to be linear. So you want to draw that. You cannot do this, right? Because the triple bond has to be linear and 180. So don't draw the alkyne like that. Draw the alkyne straight, where the atoms attached to the alkynes are linear here. Yeah. Yeah, so if you only have one EQ, you're gonna stop here, right? So that's why we need at least two EQ. So for terminal alkyne, if you have two EQ, you're not gonna have well, yeah, we're gonna go over that. We're gonna go over that for the terminal alkyne, right? Yeah. So here's the terminal alkyne part now. So now let's say that we have this vicinal dihalide, right? We're gonna do the same exact reagents, but this time we need at least 3 equivalent or excess under NH3 liquid. And then the second step, we need some kind of acid workup, like water or H2SO4 or H3O+. Okay. So the mechanism is going to be the exact same. We're going to do E2 for the first step. So let's say we bring in the strong base, NH2 minus. That's going to grab this beta hydrogen, form a double bond there, and kick out that good leaving group there. That forms this double bond after the first elimination reaction, and we still have that bromine right there. We could do another E2 reaction because we have another hydrogen here, where we're going to bring in our second equivalent of it, grab that hydrogen, make an extra bond there, and kick out that bromine there, right? Which gives us this terminal alkyne. Oh yeah, so let me show you what the difference between an internal alkyne is and a terminal alkyne is. An internal alkyne is when we have a triple bond in the middle of the chain, right? A terminal alkyne is when we have the alkyne at the end of the chain, where the terminal alkyne always has that SPCH bond right there. Because it's always at the end of the chain, it has one hydrogen. Internal alkynes has no SPCH. Terminal alkyne has one SPCH, where that one SPCH is acidic. So since we know that this SPCH is acidic, another NH2 minus is gonna grab that H and form our alkyne anion, giving this carbon here on the alkyne a negative charge after it gets deprotonated. This is the conjugate base of this acid here. Yeah. Yeah, it will not matter in this case. You could either do which one here. You could grab this hydrogen to make a double bond there and kick that out, or you could have grabbed that hydrogen right there, make a double bond there and kick that out right there. Yeah, it doesn't matter. Yeah. And that's the end of the first step. Now we bring in our second step of acid workup, where we could use water to protonate that negative charge and get our alkyne, terminal alkyne back. A lot of people get confused on like why this step has to happen, because we could have just stopped here to get the final product, right? But once this gets formed, the NH2 minus is going to deprotonate that right away because there's a base around in the solution. And then people might say, why can't we use like 2 EQ, 2 equivalents instead of 3? Because the first equivalents made the first double bond, and then the second equivalents made the triple bond here. So if we use 2 equivalents, right, we will not convert all of the vicinal dihalide into the terminal alkyne. because some of the NH2 minuses will actually deprotonate the terminal alkyne hydrogen and give that negative charge there and a mix of starting material here. But we want to convert all of the starting material into this here. So that's why we need an excess of base, at least 3 equivalents, to go all the way to this conjugate base, and then we protonate that conjugate base to the terminal alkyne there. So for terminal alkyne, the important thing to remember is that we need at least 3 equivalents of base. Yeah. Oh, right. So what prevents it is that we're gonna we form NH3 at the point NH3 liquid, and we also reacted with all of the starting material. So there's gonna be less base, and then after we wait for a while, we bring in the second step by putting some water in it or some acid. Yeah, until we get all of this, and then there's no more base around, and we just have that. Right? And then we put acid in it to protonate it to the desired terminal alkyne. Yeah. Yeah. Yeah, that's good because this negative charge here is a nucleophile. This can attack any electrophile like a haloalkane, carbonyl, epoxide, and we're going to go over that today as well. But here, this is just getting protonated to get back to the terminal alkyne. Yeah. In this solution, there's no other electrophile, so it won't attack something else. Yeah. So now, an alkynyl anion is the conjugate base of this terminal alkyne here, where we know that this is an acidic hydrogen. So if we put any strong base, we are going to form this alkyne anion here, right? And that strong base could be NaNH2, which is the most common one, NH3 liquid, or it could be a hydride ion, NaH, or you can see LDA, or you can see any of the organometallics like Grignard reagent, RMgX, or RLi. All of these here are strong bases that will rip off that proton and form our conjugate base here. And from that alkyne anion, we could do a lot of reactions because this alkyne anion would be strongly nucleophilic and basic. Okay. So let's look at the 5 different reactions you could do. The first one is going to be an acid-base reaction. So if we put water or some kind of acid, H+, we are going to protonate that alkyne anion and get our terminal alkyne back. Where this first reaction is called an acid-base reaction. The mechanism for that looks like this, where we have that strong base. Let's say we have H3O plus as the acid. That negative charge is going to grab that hydrogen and kick out that water to form this terminal alkyne here and water side product. Acid-base reaction, where this is our base, this is our acid, this base gets protonated, this acid gets deprotonated. First reaction, acid-base reaction. Okay, let's look at the second reaction. The second reaction is going to be an SN2 reaction, where we're going to need a methyl or primary unhindered substrate. So for an example of that would be something like this. And we are going to form this. Let's say this was a star carbon. Which atom here is our electrophilic atom? Which atom is the most partial positive? Yeah, the rightmost chlorine, because it is attached to the electronegative atom there, bromine. Bromine is stealing its electrons, making it more positive. Right? So that's the dot carbon right there. Star carbon make a new bond with dot carbon. And then we draw what is attached to dot carbon. This is an SN2 reaction, right? Where the mechanism looks like this, where we have, what was the thing right here? Okay. 1, 2, 3, BR. Nucleophile, attack electrophile, kick out the leaving group, make a new bond between the star and dot atom, draw what is attached to the dot atom, which is that right there. And we have a Br minus floating around because it got kicked out. This is an SN2 reaction. Where, yeah. Yeah. Right. So that is going to be something like this. Like, let's say we have this haloalkane. We know that that carbon is partially positive because that electronegative atom is withdrawing its electrons, making it more positive. If we put this through Mg and some kind of ether solvent, that Mg is going to do an insertion reaction, where it's going to insert itself between that carbon and bromine, giving us MgBr here. A way you can think about this is that carbon is more electronegative than magnesium. Yeah, so it will have a partial negative this time. Yeah, right. It turns from an electrophile to a nucleophile. And this is a Grignard reagent, right? Now, the third reaction that this alkyne anion can do is an E2 reaction, where if you have a primary hindered, secondary, or tertiary substrate, we are going to form a double bond. That plus the terminal alkyne, E2. Right. So the mechanism of this E2 reaction is like this. Okay. We have a strong base, strong nucleophile, a secondary substrate, and if we look back at like the magic table, you will see that this reaction is E2 reaction, where we want to look for the most substituted beta hydrogen, which these are our two choices. The most substituted one is the rightmost one, where this alkyne will not act as a nucleophile, but it will act as a base and grab that beta hydrogen, form a double bond there, and kick out the leaving group for an E2. So we form that alkene, and then the alkyne becomes neutralized here. So that was E2. And then the last two, he said he will go over that at the end of 118b, but it is very similar to what we have been doing, where this is going to be the same kind of attack, but we're going to have a carbonyl, which is a carbon double bond oxygen, a ketone in this case, and an acid workup. Wait, so let's just go over the mechanism of what that would look like here. So this is our nucleophile, and let's say we have this ketone here. Which one of these atoms on the ketone is the most partial positive? Yeah, this carbon right here connected to the oxygen is the most positive because it's just directly attached to the oxygen. So let's say that that is our electrophile. This is our nucleophile here. This nucleophile is going to attack that electrophile right there, right? But this is going to be a problem because it can't stop there. When this star makes a new bond with that dot, this carbon will have 5 bonds because it already has 4 bonds. 1, 2, 3, 4, and then the 5th bond with that carbon there. What can we do to maintain the octet rule? Yeah, right. One of the bonds here, its 2 electrons are going to kick up to that oxygen right there. So we're going to do that arrow there. 2 electrons are moving onto that oxygen. So once we connect it, star connect to dot. And then this dot is attached to an ethyl group, a methyl group, and now an O- group. Where that's the end of the first step. Now we bring in our second step, some kind of acid workup to neutralize this O- and give us our final answer here, right? Where this was our dot carbon, star carbon. And this reaction is nucleophilic addition to carbonyl, where we added that nucleophile to that carbonyl. And the last reaction that this alkyne anion can do is an epoxide opening reaction. So if this alkyne anion has a negative charge, are we in acidic or basic conditions? Yeah, so acidic conditions would be if everything is positive charge or neutral. If we have a negative charge in the solution, then we are in basic conditions. This second step here comes afterwards, after everything, right? So right now we just focus on the first step, which is just the epoxide and that negative charge alkyne ion, which makes this basic conditions. And if we are in basic conditions, do we want to attack the more or less subside of the epoxide? Yep, less subside, right? So this nucleophile here is going to attack that less subside, pop the double bond, and double bond, pop the epoxide up, and get us this thing, star, dot, new bond between star and dot. That dot is attached to this carbon with the wedge methyl, which is attached to O minus, right? This carbon right here with the wedge methyl is that carbon right there with the wedge methyl. And now this bond right here stays the same, and this oxygen gains a negative charge from opening up the epoxide here. Now we bring in the second step of acid workup and neutralize this O minus. To give our final answer here, where this reaction is called epoxide opening in basic conditions. Okay, so that is going to be this right here. Oxide opening, basic conditions. Okay. Now let's go over the reduction of alkynes. So there's going to be 3 different reagents here. If you have H2PDC, what was the name of that reaction in the alkene chapter? And what did it do to the alkene if we had H2PDC? Right, hydrogenation, which adds hydrogens to the double bond and makes it cis or trans if we had an alkene. Yeah, so is this syn addition or anti-addition? Syn addition, right? So when we put it on the same side, the alkene is going to be cis, forced to be cis, right? The intermediate is going to be something like this because the hydrogens are forced to be on the same side, right? So they both have to be on top like that, which is going to be that cis intermediate right there. But this H2PDC here is really reactive. It will keep going and go all the way to your alkane, right? Because it will react with that alkene again to give us our alkane right there. Where those carbons will now have these hydrogens here. And these hydrogens came from the H2. Yeah. Because think of it as bubbling H2 gas into the alkyne with the metal. There's a lot of gas floating around. But when it reacts with the metal and the alkyne, there's still other H2s floating around. There is a way to stop at the cis alkene though. And that's to slow the reaction down by using a poison catalyst, which is Linois catalyst. Right? So if you see H2 with Linois catalyst, think of a poisoned catalyst, which slows the reaction down. that will make your cis alkene. If you wanted a trans alkene, then you use a reaction called dissolving metal reduction, which these are the reagents here. Dissolving metal reduction. Right. So the first reaction gave you an alkane. The second reaction gave you a cis alkene. The third reaction gave you a trans alkene. Okay. Now let's go over the mechanism of the dissolving metal reduction, where there are 4 steps. The first step is a 1 electron transfer. So let's say that we have this alkyne right here. The metal could either be sodium or lithium radical, right? This one radical here is going to add 1 electron to one of the alkyne carbons there, right? When that happens, one of the bonds in the triple bond is going to move its 2 electrons to that carbon right there, right? When that happens, we are going to get this here, where we see that this carbon now has a radical because that sodium radical gave that carbon a radical. The other carbon here has a full lone pair and a negative charge, where that full lone pair came from one of the bonds of the triple bond there. And that's why that triple bond got converted to a double bond, because one of its bonds gave that carbon a lone pair. Do you guys know the reason why it prefers to be in this trans configuration here? Yeah, more stable, less steric hindrance. That's right. Trans to avoid steric hindrance, more stable. The second step is protonation, which we could use the NH3 liquid to protonate that negative charge. Give that negative charge a hydrogen, which is this hydrogen right here. And the third step is a second 1 electron transfer, where we're going to bring in a second equivalence of sodium radical metal. Right? Where that sodium radical is just going to give that carbon another electron, making that carbon negatively charged. Right? So this is the second step. This is the third step here, where we are going to give that carbon a negative charge there. And now this is the fourth step here, the second proton transfer. So we're going to bring in another NH3 liquid to protonate that negative charge and get to our neutral trans alkene there. Final answer. Right? And you notice how we needed at least 2 equivalents of the sodium metal or lithium metal. The first equivalence was here. The second equivalence was here. So you need either 2 equivalents or excess for this to happen. Now let's do some practice problems here. Let's take 10 minutes to this and I'll walk around. How was the midterm? Those stuff. Yeah. So tired. Yeah, yeah. Yeah. For which question? NH3. Oh, yeah, that's a liquid. Yeah. That's the L, a curly L. Yeah. Liquid ammonia. For the first problem here, what is going to happen to this internal alkyne? What reagent are we using and what is it going to make? Yeah, dissolving metal reduction, which makes the alkyne into what kind of alkene? Cis or trans? Trans, right? So the answer here is this. You don't have to draw out the mechanism. Just predict the products here, where to do that, we could number this 1, 2, 3, 4, 5 there, where there's a triple bond between atoms 3 and 4, which is why the trans alkene is going to be between atoms 3 and 4. So for predicted product questions, you don't have to draw out the mechanism. You just locate where your alkyne is and convert that alkyne into the trans alkene. How about H2 Linwise catalyst? What would that do to the alkyne? Yep, make it into a cis alkene, where we have an alkyne between, let's say, atoms. Like the way I'm numbering it is not for nomenclature, it's just for to keep track of like where the triple bond is. So the way I numbered it, the alkyne is between 3 and 4, where the cis alkene has to be between 3 and 4 as well. Right, 1, 2, 3, 4, 5, 6, 7, 8, and it has to be in the cis configuration here. Now, the next one, what is this next one going to do here? This is a tricky one. Yeah, the NaNH2 is a strong base. So Na here is going to be the ion, NH2 is going to be the ion, NH2 minus is a strong base, but we don't have any strong acid to deprotonate because this is an internal alkyne, right? And all the other hydrogens are sp3 hybridized. This is not dissolving sodium metal, so this is no reaction. because that is not a sodium metal with NH3 liquid. This is NaNH2 with sodium liquid. NaNH2 is different than sodium metal. NaNH2 is a strong base. Sodium metal is a reducing agent. Okay. So since we said NaNH2 is a strong base, what is going to happen in the first step? Which is our most acidic hydrogen here? Yep, the terminal alkyne hydrogen, where that terminal alkyne hydrogen is going to get deprotonated by the strong base NH2 minus and form our alkyne anion here, where we have a negative charge on that alkyne. And now this is our nucleophile, where we can bring in our electrophile here in the second step, which is going to do, since this is a primary unhindered substrate, this is going to do what kind of reaction? SN2, right? Because we have a nucleophile and a primary unhindered electrophile. Star the nucleophile, dot the electrophile, make that new bond between them. Star and dot, kick out that leaving group. That dot is attached to this R group right here. Final answer, where we made an internal alkyne. This was a terminal alkyne, but we gave it an extra R group by deprotonating the terminal alkyne to make the nucleophile, and then using that nucleophile to react with a haloalkane, and then that extended the alkyne to make the internal alkyne here. Okay, so the next one right here, we still have a terminal alkyne where the strong base is going to deprotonate it and give us this alkyne anion here, which is the nucleophile. And here we have an epoxide. So which carbon of the epoxide are we going to attack? Yeah, the left subside, where this nucleophile attacks that left subside, kicks up that bond onto that oxygen, and this will invert stereochemistry as well. This was a wedge bond. We're going to make this into a dash bond. So let's draw in that structure. Dash bond to the triple bond, which is bonded to that methyl. This bond here stays as a wedge because nothing touched that carbon right there. So that wedge bond stays as a wedge. The methyl stays as a dash. And now we bring in our third step, the acid workup, to protonate the O minus and neutralize it, giving us this protonated OH neutral and that alkyne that attacked right there. For the next one, we notice that for synthesis, we have to see what's the similarity and differences between these two. We had 1, 2, 3, 4 carbons in the reactant, but in the product, we only have 2 carbons. What is one reaction you guys learned that cuts up things? Ozonolysis, that's right. So we could go backwards and say that this last reaction was ozonolysis, which came from that double bond right there. Because if we made that cut between the alkene, we would get 2 of these here. What is the reaction that we just learned that will convert an alkyne into an alkene? There are 2 ways. Yeah, the Na metal radical with like at least 2 equivalents with NH3 liquid to get that alkene, or we could have used H2 Linois catalyst to get the cis alkene. But any of these alkenes cut up will give you this product there. So you could have cut up this cis alkene or this trans alkene. That gives you the exact same product here. Now let's move on to the next alkyne reaction, which is going to be very similar to all the alkene reactions we've been doing. This is going to be addition of HX now, where let's think about the mechanism. Let's say we have this terminal alkyne and we put that through HX. This is a strong acid, so we want to make the more stable carbocation, which is the more subside, right? If we want the carbocation to be on the more subside, the less subside has to grab the H and kick up the X, which is either going to be bromine or chlorine. So this less subside grabs that H, kicks out that X, and we are going to have this intermediate right here, where one of the bonds of the triple bond grab that H, which is now that bond right there. Since we got rid of one of the bonds, that becomes a double bond right there. This carbon right here used to have 4 bonds, 1, 2, 3, 4, but now it lost the bond. It only has 3 bonds, which is why it has a positive charge. Now that positive charge can get attacked by the X minus right there. Right. Once that happens, we have an X right there. So that is going to be your answer if you have one equivalent of HX. If you have 2 equivalents or an excess of it, we're going to do this reaction one more time. The less subside grabs the H, kicks out the X. And now we have a positive charge on that carbon, where the X minus that got kicked out is going to attack that positive charge, giving you your final answer if you had at least 2 equivalents, the geminal dihalide. Right. So if you have at least 2 EQ of HX, you will get to your geminal dihalide there. Right. Yeah. Oh, Pascal said that? Oh, Helix said that. If the instructions say assume excess unless otherwise noted, which is what Nisiri does, then you could assume it's an excess. But if he explicitly writes out 1 equivalent of HX, then this is your answer here. If he writes out 1 EQ on the arrow, 1 equivalent. But if he just puts XS, then you assume that we have a lot of them and we end up here. Yeah. And that was the terminal alkyne example. Let's go over the internal alkyne. And we can have 2 different types of internal alkynes, an asymmetrical one or symmetrical one. Asymmetrical one is when the 2 R groups are different from each other. Right. So we are going to have 2 different products here. One of the products is going to be, let's see, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, where the X's are on that carbon. The other product is when we have the X's on this carbon here. Right. So here's the mechanism of that. Like, let's say we have HX, right? We notice that these carbons here are equally substituted. There's no less substituted carbon and there's no more substituted carbon. They're both equally substituted. So either carbon could grab the H and kick out the X. Let's say that this carbon here grabs the H and kicks out the X. That would form this positive charge on the other carbon, right? Where the X minus is going to attack that positive charge. The same thing happens like over and over again, like based on what we did previously. That's the answer if we had 1 EQ. Right. We're going to do this reaction one more time, where now it does matter where the carbocation is. Which carbon of the alkene is going to be more stable? The one here or the one right next to the halogen? So this one here would be secondary. This one here would be tertiary, and it's going to be stabilized by the halogen as well. Yeah, it looks like it's destabilizing it, but it's actually donating electrons into the thing, into the carbocation, making it more stable. Right. So a carbocation underneath a halogen is actually gonna be more stable. Yeah, they can also donate electrons with its lone pairs of electrons. Right. Because let me show you what that means right here. Like, let's compare this positive charge with this positive charge right here. We know that this positive charge cannot do resonance, so it's stuck there. But the positive charge on the left side, yeah, it could take that lone pair. Okay. And since this is resonance stabilized, this positive charge here is more stable than this positive charge. Okay. So that's why on the other end, we're gonna grab that H and kick out the X. And that's gonna be a positive charge under there, where the X minus that got kicked out is gonna attack that positive charge and give us this geminal dihalide there. Right? Yeah. Oh, halogens are worse than having carbocation. Right. Halogens are better getting the negative charge because they are more electronegative. The carbon here is better because it is less electronegative. Right. Wait. Oh wait, actually, wait. So you know how these are the two resonance structures, right? Which one is the major resonance structure? Which one is more stable? You know how there's different factors? Full octet. Yeah, that's the number one priority for resonance. All that single atoms here have an octet rule. This carbon here does not have an octet. Right. Since this is minor, does that make it more or less reactive? If it's less, yeah, more reactive because it's more unstable. And since this is more reactive, that's why this is the one being attacked by the X minus. This is more stable, so the X minus doesn't attack the more stable one. It attacks the less stable one. Right. Okay. So that's how we get to that unique product. But we could have also had another product if, let's say, we grabbed the H from the other side of that kind. That's gonna give the exact same like mechanism, but different spot. Positive charge there, X minus attacks that positive charge. Second equivalence of HX. Positive charge under the X, and then the other X minus attacks that positive charge, giving us this geminal dihalide here. So we get two different products here because we have two different carbons of the alkyne that are equally substituted. So if we had a symmetrical alkyne, we only get one product, right? Because both carbons, if we put X's there, they're going to be the exact same thing. That is the same exact thing as this structure here. It's just flipped and rotated, right? Where these carbons here were the carbons of the alkyne, but since this is symmetrical because they have the same R groups, they are going to be the same exact structure there, right? Where the mechanism is going to be very similar as what we did previously. Where one carbon is going to grab the H, kick out the X, form this intermediate. 1, 2, 3, 4, 5, 6. 1, 2, 3, 6. Positive charge here. X minus attacks that positive charge. Right. And then we bring in another HX here. And then positive charge here. And then X minus attack positive charge. And then we get this geminal dihalide, right? Okay, so now let's do addition of X2. Where if we have two equivalents or excess, we are going to have these products here. Oh, this one product here. Where halogens are going to attach on both carbons of the alkyne excessively. Right? The first equivalent of this X2 is going to add X on both carbons with an alkene there. Second equivalence will react with that alkene and add another set of X on both carbons. So here's the mechanism. Right? Let's say we have X2 floating around, like Br2 or Cl2. Think of this as an alkene reaction here. What kind of intermediate is going to be formed? Yeah, a ring where one carbon is going to attack that X, kick out the other X, and at the same time, that X being attacked is going to attack the other carbon of the alkyne. Right? And that's going to form, say, this ring right here with a positive charge. And this right here becomes a double bond because we had 3 bonds here, but one of the bonds made that ring right there, where when we subtract one, we have a double bond now, right? So now the other X that got kicked out becomes X minus, attacks the ring, and then breaks open the ring on the other side right there, giving us this intermediate. So this is the answer for the first equivalence where we stop here. We could bring in a second equivalence and do this reaction again by bringing in another X2 and then attacking one of the X's, kick out the other X, and at the same time, that X being attacked has to attack the other alkene, making your other bromonium or chloronium ion. And then the X minus is just going to attack one carbon of the ring and break open the ring there, giving you your final answer here. So it's just the alkene reaction 2 times because we have a triple bond where when it reacts 1 time, that triple bond becomes a double bond, which that double bond can react the same exact way as what it just did. So this double bond 2 times, reaction 2 times. Yeah. Yeah, this is still anti-addition, where when we do these reactions, they are supposed to be anti to each other, but I just left out the stereochemistry, but that's good that you recognize these are anti. Yeah, anti-addition. Because when this X attacks the ring right here, this will invert whatever that was, like a wedge. Or no, oh, this can't be a wedge or dash because this is an sp2 carbon right here, right? But when it attacks here, it will flip the other side on the opposite side, right? Yeah. Okay. Let's try these 2 practice problems here. Oh yeah, and when you see CH3COOH and lithium bromide, that's just a catalyst that makes this reaction happen faster. That won't do anything in the reaction. It just makes it faster. So for this first one here, the first step, what is that going to do to the terminal alkyne, the NaNH2 NH3 liquid? Yeah, it's gonna give it a negative charge by deprotonating it and becoming this alkyne anion. Now, once we have that negative charge, what is that second step gonna do? Yeah, it's gonna attack it, kick out that iodine leaving group for SN2 reaction, which extends the alkyne to an internal alkyne there. And now the third step, HBr 2 equivalence is going to, yeah, it's gonna add bromines 2 times on the same carbon. Right. So this is the answer right here. And here's the mechanism. Wait, 1 carbon of the alkyne attacks that H, kicks out the Br, and we have a positive charge here now, where the Br minus can attack that positive charge and give us that intermediate right there. But since we have 2 equivalents, right, we want to protonate one of these carbons here. So we want to form the more stable carbocation, which is this one right here. So that means we're going to protonate the less subside right there. So the other HBr is going to get deprotonated by that carbon and give a positive charge here, where the Br minus can attack that carbon and give us our final answer here. What would this reaction do to the alkyne? Yeah, so it would make the ring first. Say Br, attack that bromine, kick out the other bromine. It becomes this Br ring, where the Br minus that got kicked out is going to attack that ring, break it up, and then have a Br here and a Br here. So that's the first equivalence. But we have 2 equivalents, so we're going to do this reaction one more time. And then Br minus attacks the ring, open up the ring, and get our final answer here. Where we have 4 bromines, 2 bromines on one of the carbons of the alkyne and 2 bromines on the other carbon of the alkyne. Yeah. Any questions on these 2 problems? This goes there. Yep. Okay, now let's go over keto enol tautomerization, where have you guys heard of the term enol before? Oh, okay. Oh, I see. Yeah, yeah. So think of it as an alkene next to an alcohol. Eno, alkene next to an alcohol. So an example of one, eno, is this right here, where we have this alkene next to an alcohol right there. Whenever we have this will always do something called tautomerization, which converts to the carbonyl form. Right? So tautomerization. And that eno converts to the carbonyl, carbon double bond oxygen form, where this carbon holding the alcohol becomes this carbon double bond into the alcohol, oxygen now. But you notice how the double bond is gone now and there's no more H on that oxygen? That's part of the tautomerization reaction, right? And this is always in equilibrium with each other, but it favors this carbonyl form because this carbonyl form is more stable than the eno form. Another example of an eno is this right here, because some people might say that for tautomerization, you always get ketones, but that's not always the case, because what if we had this eno here and we do tautomerization? We are going to get this carbonyl here, which is not a ketone. It is now an aldehyde. So if you're, it depends on what your groups are, you could either get a ketone or aldehyde after tautomerization. And there are two conditions for this mechanism, basic conditions and acidic conditions. Let's look at the basic conditions first, where let's say we have this eno right here. If we have hydroxide ion, OH minus, that is going to deprotonate the most acidic hydrogen, which is the hydrogen on the oxygen, right? When that happens, we are going to have a negative charge on that oxygen right there, right? And we see that this negative charge on that oxygen, what can it do with the alkene? Right, if it's right next to the alkene. Do resonance, right? Because that negative charge there can make a double bond between that carbon and oxygen. And then that double bond there can make a negative charge onto that carbon right there. When we do that, we have this right here, which is the major resonance structure. Yep, the first one, because the negative charge prefers to be in a more electronegative atom. All of these carbon atoms here have the octet rule, and all of these atoms here also has the octet rule. So we don't care about that. Now we care about where the negative charge is. Since the first one is on the more electronegative atom, that's more stable and less reactive. Since the negative charge here is on the less electronegative atom, that's less stable and more reactive, right? Where that more reactive negative charge is going to get protonated by water. Which is our carbonyl form of this enol here. Now let's look at it in acidic conditions. Let's say we have the same enol, but this time we have acid, H3O+. If we have acid, we have to protonate the most basic atom, which is one of these carbons here. Which carbon is going to have the more stable carbocation? This carbon or this carbon? Yep, the right one, because that carbocation there can be stabilized by the oxygen with the lone pair. So that means the left one has to get protonated. The left one here grabs the H, kicks out the water to form the positive charge there, where we said that that is stabilized by that resonance here, where we are going to have this resonance structure, where the last step is to use the water as a conjugate base or base to deprotonate that carbonyl oxygen and make it neutral. Okay. So that's the carbonyl form of that enol there. in mechanism questions, like in future reactions you learn, some professors might allow you to just convert an enol to a carbonyl and just put an arrow and say tautomerization, where you don't have to draw out all of these, but sometimes they do, but you just have to read the question carefully. Right? Where the tautomerization can happen under basic or acidic conditions. Now let's practice drawing all of these enols into carbonyls. Don't do the mechanism. Just draw out the carbonyl form of the enol. So to draw the carbonyl form, look at where your alcohol is and just put a double bond right there. Get rid of the H and get rid of the double bond. Same thing here. Get rid of the H, get rid of the double bond, and out carbonyl there. So the carbonyl form of the first and second one is the exact same structure. The carbonyl for the third one, get rid of that double bond, get rid of that H, put a double bond there. Is this. The carbonyl of the last one is this. Okay. So now let's go over mercuric ion catalyzed hydration. So these are the reagents for that hydration, this hydration reaction: H2SO4 water and HgSO4 mercury, right? And there's gonna be two different kinds of reactions that you can have: terminal alkyne and internal alkyne. So if you have a terminal alkyne, your product is gonna be a methyl ketone, meaning that you will have this as your product here. Right? Where if I number this 1, 2, 3, 4, this is this 1, 2, 3, 4 right there. Okay. So let's go over the mechanism of this. Let's say we have that alkyne. And let's bring in our mercury ion here. The mercury with the +2 charge. This is going to form the ring, a mercurium ion ring. One of the carbons is going to attack that mercury. At the same time, that mercury is going to attack the other side of the carbon. And that's going to give us this mercurium ring here with the positive charge. Right. Okay. And when that happens, now the water comes in and it is going to attack. If we are in acidic conditions, will it attack the more or less subside? Yep, the more subside. So this water here attacks the more subside, breaks open the ring onto there. Right. When that happens, we are going to get this right here, where that oxygen that attacked is still bonded to two hydrogens with a positive charge. The next step is to neutralize that positive charge by using a base like water to deprotonate that positive charge oxygen and give us this intermediate here. Okay. And what do you notice about this structure here? What is the name of this structure? Enol, right? And whenever we have an enol, we always have to tautomerize it into the carbonyl form. So that enol is going to tautomerize, which the mechanism, we're in acidic conditions, is going to be this exact mechanism here. But for mechanism questions, hopefully your professor will allow this like tautomerization like step here. You could convert that, which I see in his notes that he did, like do the same exact thing. He just went straight to the carbonyl like that. Right. And then from here, to get rid of the mercury, that bond between the mercury and carbon is going to make a double bond there. And then push this double bond onto that oxygen right there to give that oxygen a negative charge, where that negative charge can get neutralized by the acid H3O plus to become a neutral alcohol. But what did we just form again? This alcohol next to the alkene. Enol, right? Since we have another enol, we do another tautomerization step to get our carbonyl here, right? So to go from this enol to this carbonyl is the tautomerization, where this product here is called a methyl ketone because we have a ketone where one of its R group is a methyl group right there. So that's why this is a methyl ketone. And we form that methyl ketone always from terminal alkynes with the hydration. So in synthesis, if you see this feature on the product, like a methyl ketone, then you most likely had this reaction here, the hydration of a terminal alkyne there. Right. Okay. So it is going to be different if we had an internal alkyne. If you have an asymmetrical internal alkyne, right, then we could have two different kinds of ketones. The ketones on this carbon of the alkyne or that carbon of the alkyne. So we had a 1, 2, 3, 4, 5. That is 2, 3, 4, 5. We could have a ketone at carbon 3 or a ketone at carbon 4, right? The mechanism is the same as above, right? The same mechanism, but this time, you know how when we have a ring between these two here, the water could attack that carbon, becoming this ketone here, or the water could attack on that carbon, becoming this ketone here. But the mechanism is the same exact mechanism as we did with the terminal alkyne part, right? It's just the where the water attacks, which becomes this ketone here. Yeah, so it is always in acidic conditions because we are in acidic conditions here. H2SO4, right? Where that ketone oxygen, right, is this oxygen of the water there. But you know how here, oh, I think were you asking like it doesn't matter like which side it attacks? Yeah, in the terminal alkyne, it does matter. It's always the more positive, more substituted side because we are in acidic conditions for terminal alkyne. But if we are in internal alkyne, right, it doesn't matter because we have this ring right here where both carbons are equally substituted. There's no more subside. If the water attacks this carbon right here, right, we are going to have that product right there. If the water attacks this carbon right here, then we get that product right there, which is why I said it's the same exact mechanism like from here after the attack. But now it doesn't matter. It doesn't matter which carbon it attacks because they're both equally substituted. Yeah. Okay. But this time, water can attack either carbon of the mercurium ion to give mixed ketone products. That is for asymmetrical alkynes. let's say we had a symmetrical alkyne here, where the R groups of the alkyne are the same. We only get one product, which, let's say this is 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. If we put a double bond, a carbonyl at carbon 3, and we try to make a carbonyl at carbon 4, that's the exact same thing. It's just flipped and rotated, right? Like imagine flipping and rotating it. That's the exact same thing if it's a symmetrical alkyne. The mechanism is same as above, right? And it doesn't matter which side of the ring it attacks because they're both equally substituted. Okay. And now for hydroboration oxidation of terminal alkyne, you are always going to form an aldehyde. So this is always your product here. Where this is, let's say, 1, 2, 3. This is 1, 2, 3. Because for hydroboration oxidation, is this a Markovnikov or anti-Markovnikov reaction? Yep, anti, which means that we are going to add the alcohol on the left side. So let's say we had an alcohol here. This is the intermediate. But what do you notice about this structure here? Yep, eno. And whenever we have eno, we always tautomerize into the carbonyl form. Where this hydrogen here right, this hydrogen right here is that hydrogen right there of the aldehyde. Where this carbon is that carbon right there with the carbonyl. And the mechanism to add alcohol right there is that really long, like 16-step mechanism for hydroboration oxidation, which he didn't test on the midterm, which is a good thing. So I don't think you need to worry about that. Yeah. Yeah. That would have been too long. Okay, let's try these practice films for 5 minutes. Oh, the alkyne reactions. I can make some some, like, how many steps do you want it? 3? Let's see. Yeah. I'm gonna include some alkene reactions too. Yeah, try that. Yeah. Yeah. What is one way we add an extra carbon? Oh, that's Grignard, right? But there's also another way. How can we make this a nucleophile? This carbon here negative charge. Yeah, deprotonate NaNH2. Yeah, which that NaNH2 will create a negative charge here. Oh, we could do MCP on an alkene. Uh-huh. Yeah, yeah, yeah. Yeah, that's right. That's right. You got it. And once we have that trans and we do MC PBA, we get that. We go to here. Water. Yeah. The other way is you could have made the cis one using H2 Lindlar's catalyst, right? And then do osmium tetroxide. Cis, right? Which is this, but this is a single bond that can rotate. Yeah, giving that. Yeah. Okay, so for the first one, we have hydration, mercury catalyzed, and a terminal alkyne. What is that unique product that we said would be if we had a terminal alkyne with a mercury catalyzed hydration reaction? Yeah, methyl ketone, right? Where that's gonna be something like this, where we have 1, 2, 1, 2, that right there, methyl ketone. Now, this next one is hydroversion oxidation and a terminal alkyne. We have a terminal alkyne and we put that through hydroversion oxidation. What is the product that we form? The functional group of the product. Yep, an enol first on the anti-Markovnikov position, aldehyde, right? Because that enol will tautomerize into the aldehyde, right? So it will create this aldehyde right here, where before that it was this enol here, right? Because this hydroversion oxidation adds alcohol on the anti-mark carbon, the less subcarbon right here. But since this was a triple bond, we still have a double bond right there. That double bond next to the alcohol tautomerizes to the carbonyl here, which is an aldehyde. Okay. So for the next one, we have an internal alkyne that is asymmetrical. So how many products would we get if we do hydration reaction on a asymmetrical internal alkyne? Yep, 2, which our 2 separate products are going to be a mix of ketones here, where the ketone carbonyl is on either on one end of the alkyne carbon or the other end of the alkyne carbon, because they're both equally substituted, and we get a different product because these are not the same structures. They have different R groups, right? Like this ketone here is closer to this like bulky group, whereas this ketone here is further away in that bulky group. Okay. Now the next one here, we see that we have a terminal alkyne with 2 acidic hydrogens, which the first step made that one of the acidic hydrogens into a negative charge. The second step did an SN2 reaction. That's 1, 2. And then the third step deprotonated the other SpCH hydrogen to create a negative charge on that end of the alkyne. And then the fourth step did another SN2 reaction to now make the symmetrical internal alkyne. And how many products would we get if we do a hydration reaction on a symmetrical internal alkyne? Yep, 1, because it doesn't matter which carbon we attack. that's going to give us the exact same product where we have 1, 2, 3, 4, 5, 6 carbons. That's 1, 2, 3, 4, 5, 6. Where at carbon 3, we have a carbonyl there. Any questions on this set of questions? We're almost done with the alkyne chapter. There's like 1, 2, 3. Yeah, there's like 3 more after that. Yeah, it's like the really weird one, like the radical hydrobromation, alkeno organometallic, and the Heck reaction. Yeah, this is all of chapter 13 here. Yeah, but it's a lot of repeat of alkene chapter, like the hydroversion oxidation, HX, X2, hydration with mercury, right? But the next session, we'll move on to chapter 14, the conjugated one. Okay. So the next reaction is radical hydrobromination of alkenes, where when you see HBr with ROR, what kind of reaction does that do? Markovnikov or anti-Markovnikov? Yeah, anti-Markovnikov, where we're going to add bromine on the left subside. And in this case, since we have a double bond, we could have a trans alkene or a cis alkene. Right. So the mechanism is the same as the last alkene reaction. There's 2 steps, initiation and propagation. So let's look at initiation. The peroxide bond, ROR, it splits into 2 OR radicals because that bond between the 2 oxygens is really weak and unstable. That's initiation substep A. Initiation substep B is that we bring in one of the OR radicals that we formed in substep A and react that with the HBr. The H bonds with the OR radical, and then a Br radical is formed. So we have alcohol and Br radical. Once we have this Br radical, then we can do the propagation step. Like everything is going to happen a lot of times now. So now we bring in our propagation step. You didn't test this mechanism too on the midterm, right? The mechanism was like the X2 or like the Br2, CO2 with water on the exam. What was the mechanism reaction? Oh, I think that's synthesis, right? Isomerization and then CO2. But the mechanism, like the arrow pushing stuff, like they give you the reactant, the reagent, and the product. What was that reaction on the exam? Oh, so it was the hydration. Oh yeah, the one with the optical thing. So yeah, so hydration reaction, that's H2SO4 and heat. Yeah. Right. For propagation here, let's bring in that Br radical. And now the alkyne that we have in the starting material. Which carbon of the alkyne is going to give us the more stable radical? Yeah. They give it as a carbocation. Yeah, the leftmost. So we want the radical here. That means that the bromine is going to attach on the left subside. This is why this is anti-Markovnikov, because that would give us the more stable radical here, right? When the bromine attaches, it could attach on the top side, giving a trans alkene, or it could have attached on the bottom side, giving us a cis alkene right there. Right. Okay. The next thing here is to get rid of that radical by putting an H there. Right. That radical could get an H from HBr, but that makes another Br radical. So that's the final mechanism where we have Br radical that gets reformed, and this Br radical keeps going on and on and on and on until it gets to the termination step. Right. So we can have a trans alkene or a cis alkene with the Br under anti-Markovnikov position. Right. Now the next one is a 118A like reaction where we have Br and Mg. What would that create? What kind of reagent? Grignard, right? It's going to create MgBr, where which atom is the negative charge atom? Oh yeah, bromine is like also negative charge, but what is the nucleophile here? What is the one that is going to attack electrophiles? So Mg is like making this carbon here attached to the Mg, the nucleophile, because you know how whenever we have a Grignard reagent, like let's say this, the carbon that is attached to the Mg is always the one attacking the electrophile. This carbon right here attached to the Mg is the nucleophile, right? Whatever is attached to the Mg is always the negative charge nucleophile right there. So this negative charge nucleophile can do the similar reactions as we did in the alkyne anion, but this time the negative charge is on that carbon right there that's attached to the Mg. So we could have, let's say, this star attached to that dot. The mechanism is the exact same as the alkyne anion. Star dot. And since this is a negative charge carbon, are we in acidic or basic conditions if we have negative charge conditions? Basic, right? Which attacks the less subside of the epoxide, right? So that's going to be that right there. The mechanism is the exact same as we did at the very beginning with the alkyne anions. Like, what is this reaction here? The very top one, the reaction name. Like, what happened in the first reaction? Yeah, SN2, SN2, right? Because this is our nucleophile here. Our nucleophile attack the electrophile, kick out the leaving group, right? SN2. Right. How about the second reaction? What was the name of the second reaction? Oh, this is kind of a new one because of the carbonyl. Nucleophilic addition to carbonyl, right? Because the nucleophile here attacks that carbonyl carbon, pop the double bond onto the oxygen, which becomes O minus, and then that O minus becomes OH by the acid workup. The third reaction name? Epoxide opening in basic conditions, right? Where the nucleophile here is this carbon, it attacks the less subside, break open the epoxide, giving that OH right there. Right? Same kind of reaction and mechanism as the very beginning, but this time our nucleophile is different. Our nucleophile is this Grignard reagent here. Okay, okay, last reaction of this chapter. Yeah, it's a long thing, but after this we're done. We're done. Yeah, yeah. This is early because the thing he ended on today was he didn't complete the mechanism. Was yeah, today after the midterm, like I think he gave you guys an hour and then after last 15-20 minutes lecture time. Yeah, yeah. This is where they ended right here. This hydration mercury thing. Yeah. Yeah. You guys will probably finish this next lecture, like all of chapter 13, and then move on to the next chapter. Yeah. Last one. Let's see. So for this Heck reaction here, you're gonna see a metal like palladium, Pd, or nickel, Ni. Which one of these substrates has a good leaving group? Would it be this alkene or that alkene? Yep, the left one. So I'm gonna highlight that carbon holding the good leaving group yellow. Now let's look at the right side, the other alkene. We are going to focus on the less substituted side of the alkene right there, right? Yeah, we're going to make a new bond between the yellow and blue highlighted atoms and get rid of the Cl. So this is our product right here. Right? Where this was the yellow highlighted carbon, this was the blue highlighted carbon, and this is the new bond between the yellow and highlighted carbon. The Cl gets kicked out in the mechanism, which I'm about to go over. Right? this right here, the yellow highlighted carbon, is the substrate with the good leaving group. The blue highlighted one is the less subcarbon of the alkene. Right? Where another way to keep track of everything is we could say this is 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Like that. Okay. Now let's go over the mechanism. Let's say this is the alkene with the good leaving group here. The metal, let's say palladium, is going to do an insertion step. It's going to insert itself between that carbon and chlorine right there. This here is the insertion step. Yeah, kind of like MgBr, like how Mg inserts itself between carbon and X, like Br. This palladium is inserting itself between that carbon and Cl. Now, once that happens, we have this PDC Cl. Okay. Now, let's bring in our other alkene here. Okay. Now, think of this carbon here attached to the PD as a negative charge, like a Grignard reagent, right? That carbon is going to attack the less subside of the other alkene. And at the same time, the more subside is going to attach onto the palladium. When that happens, we are going to get this alkene, the new bond here, and then we have that. Where the alkene of the pink substrate is gone. And then we have the palladium is attached to this more subcarbon right here. And then it's attached to Cl. Okay. Does this make sense on how I got to this here? It's a little weird because there's a lot of like things moving around. Let's see. Yeah, you could think of it as like less sterically hindered and more chance of attacking that side, which gives this carbon here a negative charge, where that negative charge on the more subcarbon is less stable, more reactive, right? Which attacks the palladium there. We see that this carbon here, the more subcarbon, attacks the palladium, which is this new bond right here. The more subcarbon is now attached to palladium. The double bond disappeared because that double bond right there made that new bond between that carbon and palladium. Oh, this one? Oh, so that bond, it just, let's see. Oh, that bond right there, it made a new bond between that carbon and that carbon right there, right? This double bond here on the blue substrate is still there, which means that that double bond wasn't used to make that bond. Yeah, what was used to make that bond is that bond right there. But you know how this double bond disappeared right there on the pink side? That thing came down to make a bond with the palladium right there, right? Where this bond between carbon and palladium made that bond right there. So to summarize everything, palladium insert itself between carbon and Cl. This bond right here between carbon and palladium makes this bond right there. And then this double bond right here on the other alkene makes a bond between that carbon and that palladium right there. Right. Now, from here, we are going to reform the double bond between that carbon and hydrogen. Give that palladium a lone pair of electrons, and then kick out the good leaving group chlorine there. Right. Yeah, when I have it on my like notes, like I just see it as this right here. But like professors don't usually test this mechanism because it's like more metal inorganic chem stuff, right? So I don't think he'll mascot will test it too because he didn't test the hydroversion oxidation. So hopefully this is not gonna show up. Yeah, this is more inorganic chem because it's more metal stuff. where palladium gets kicked out as a side product and HCl gets kicked out as a side product, where HCl comes from this H and Cl there. Because when Cl leaves as a Cl minus, and then the H will leave as a H plus. The Cl minus can attack the H plus. Yeah, with a positive charge. Oh, okay. I think what I think might have happened is that you know how when the Cl leaves, right? When the Cl leaves, it leaves with a negative charge. It just deprotonates that H at the same time. So all of these are happening at the same time here. Right. So the thing that is deprotonating that is a Cl minus, which becomes HCl, and then that does a like E2 like reaction here. Yeah. But I don't think this will get tested. Like this mechanism, I don't think it's gonna get tested. But that's where these side products come from. Yeah. That's interesting. Like I didn't think about it like that, but now like it makes more sense now. Yeah. Okay, that's it. That's all the reactions. Let's just try these practice problems and I'll walk around. I know. Yeah. Or we can just like take a break or something. Give the answer? Okay. Yeah, I'll just write the answer down. And then you guys try it though, and then like if it doesn't make sense, I'll explain the process as well. Yeah. But that is all of chapter 13. Almost. The conjugated systems, like resonance, allylic positioners, and then thermodynamic kinetic thing, and then benzenes. Yeah, that's the best part of 118B, the benzenes. Yeah, that's the favorite synthesis, like kind of reactions. Yeah. Heck reaction, yeah. Nusiri doesn't test on heck reaction too. Nusiri and Helix, yeah. I just went over it just in case. Just in case Pascal goes over it, yeah. Yeah. Mm-hmm. Yeah, it could work with BR or I or OTS or OMS. This chapter here was supposed to be on the first midterm, but he didn't have time to finish it. Yeah. Yeah, he wanted to put it on there. Yeah. I know, like no time to practice. And Alkyne. Yeah. Yeah. Yeah, he's like, I'm gonna be the other Nobel Prize winner with you. It's like if you find out something. Probably because that was all I have planned. Unless like there's other questions, like all of chapter 13. Like I didn't expect to finish all of it like to this session, but I think it's because there's not a lot of people here and like not a lot of questions, so I just like I blitzed through it. Yeah. Yeah. I know. Like, there were no more like desks open. Yeah, Katie was watching me over there. She was sitting over there. Yeah, but she told me that she like wanted to leave because she wanted to like save seats for like the other people coming in because like there were still people coming in. I don't think so. Yeah. But these like desks here were taken like the side desks. Yeah. Yeah. I think she told me she took a picture of the whole thing. I didn't see. Yeah. And she came to them, she was like, this is also yeah, like she I told her like I think it's because like they had the test this morning and then she was like, oh, that's why. And then I told her like I think there's not gonna be a lot of people like today because they just finished the test. Yeah, that's why, yeah. Yeah. So the first reaction right here, we had a terminal alkyne and HBr with ROR. When you see ROR, always think anti-Markovnikov, which adds the bromine to the left subside right here. And when we did mechanism, we said that it could have been a trans alkene or cis alkene, which is why we have two different products, one trans, one cis. For the second reaction is the Heck reaction, which Helix didn't test it, Nasiri didn't test it, but I don't know about Pascal. But what you do is you find your alkene with a good leaving group, highlight that carbon, and then on the other alkene, highlight the carbon that is less substituted, which is this one right here. And then you just make a new connection between them and get rid of the Cl. Right. And then this is the other Heck reaction here, where let's highlight the carbon with the good leaving group, which is that one, and then highlight the carbon that is less substituted, which is that one. So we make the new bond between the highlighted carbons, right? And then we have to make it trans because it decreases steric hindrance, more stable. We didn't want to make it cis because that is more steric hindrance and more unstable, right? And also this alkene here, we see that these two ethyl groups are cis to each other. So we want to maintain that cis relationship between the ethyl groups. Yeah, that's it. And then the last one here. So let's do this step by step. What this did was anti-Markovnikov HBr. So we could have had trans, or we could have had cis anti-Markov HBr, where when we did Mg, that creates our Grignard. Yeah. Negative charge carbon there. And then that Grignard here, the carbon attached to the Mg is the nucleophile. It attacks this positive charge carbon and then kicks out the bromine to get these two products here. Uh-huh. Yeah, that's right. That's why they're separated. This is a stepwise predict the product question, where if you see like different steps, 1, 2, 3, 4, you focus on one reagent first, what it does to the reactant they give you, and then look at the product that they give you. And then now this product is the reactant for the next step, the second step, right? And then once you do that, that product there is the reactant for the third step, which does an SN2 reaction. First step was anti-Mark hydrobromination. Second step, Grignard reagent formation. Third step, SN2. And that's it. Yeah, that's it. That's it. Yeah. How about